So just a quick survey before I start. Can I see by show of hands, has anyone ever heard of formal verification before? Okay, this is a good start. Has anybody not heard of it? Okay, we'll let the record show the number 0 here. Next question, has anyone ever used formal verification? Okay, that may be about 40% here. Okay. Now, next question. Who thinks their design that has never been formally verified works? Ooh, oh, you're going to get yourself in trouble with that one, aren't you? Okay, we'll say about 12 people there. And, okay, 2 more. Has anybody ever read the ZipCPU blog? Yes. Hey, I've got a little bit more than 50%. We'll say maybe 60%. Okay, now I'm going to be surprised if I get much of a response on this next one. Has anyone tried the ZipCPU? Hey, I got 1. I am so good. Okay, those are my quick questions here. So I want to talk just a real quick, what is formal verification? I've only got 2 slides on that. Looks like you guys have all heard about it. My goal was to formally verify the ZipCPU. So I'll spend a moment, I'll say here's what I expected before I start. And then I'm going to talk about a bunch of things, you know, sort of lessons learned as I went through different types of components about doing this formal verification. And finally, I have no shame. I will tell you the bugs that I found and fixed using formal verification. Things that none of my test cases ever found. Hopefully you'll get a little interested by that. And like I said, I'll be lessons learned along the way. Whoever's got my time, if I start running short on time, I'll scoot through these lessons learned. You can read them in the slides later. Okay. There's 3 basic types of formal verification properties. There's the assume statement, which tells the solver, if this isn't true, don't even bother looking at it. There's the assert statement, which says if you can ever make this false, you win. It's almost like a competition. The guy's really out to get you. And then the third one is a cover statement where you prove that something can happen. Okay? Basically, you can sort of state it as, given that my assumptions hold, prove that my assertions hold. Sort of the basic idea behind it. As one person said when I taught a course on formal verification, he said, the solver is really quite a bastard, isn't he? Yes, he is. He is out to get you every way he can, and that's just sort of the way to do it. The other thing you need to know is there's this past expression, which gives you the value of whatever was inside that X 1 clock ago. Okay, these are the basics. You can do a lot with those basics, and these are what I used for the ZipCPU. Okay, the next thing you need to know is there's 2 basic, well, there's a third, but I'm not going to cover it. 2 basic ways of using the formal tools. The first one is a bounded model check. This bounded model check will start at time 0, and it will go how many steps to go into the future. That's number 1. The second type you can do is what's known as K-induction, where you say, if I find any place where all my assumptions hold, all my assertions hold, that same number of steps, find if you can make it fail at the last one. Okay? They're very different types of proof, although there is the mathematician will say, you know, for a given length, there is a length where BMC and induction are equivalent. That's as far as I got in the paper before I got lost. The big thing to know about the difference between the 2, BMC, you can do really, really simple properties. If you want to pass induction, you've got to have invasive properties. You've got to get into your design and you've got to tell the engine, this is what can never happen. You can do bounded model checks on black boxes. If you want to do the induction, you've got to get in there. It's more of a white box test. An example of a bounded model check of a CPU is the RISC-V formal approach. Because it's a bounded model check, it can really work on lots of different types of CPUs. The proof I used for the ZipCPU is very specialized to the ZipCPU. It's an induction test. Takes a little bit of time to do that. BMC, it'll find failures. Induction will prove the properties for all time. Right? They both have their purposes. I'm just drawing a couple differences between them. So before I got started with working on the ZipCPU, I had formally verified all the components. I had verified several of the peripherals, timers, counters, interrupt controllers, components. I verified the prefetch, the instruction cache, the decoder, the ALU. I'll discuss some of these along the way. You know, I'd gone through all this simple stuff. Why? Because the big thing was intimidating. All right, let's be honest. That's why I was worried about the big one. Only the top level of the CPU remained. Initially, I was concerned with pipeline bugs, like instructions that would vanish as they went through the pipeline because some following instruction passed it. I was concerned with instructions that might get duplicated, or anything where a register would be written to and it wouldn't get propagated through the CPU. This is what I was expecting. You'll get to see at the end what I actually found. If you're not familiar with the ZipCPU basically has, let's see, 5 pipeline stages. There's the prefetch, the decode, the read operand stage. I'll show you that in a moment. And then there's this execution stage where there are 4 different types, ALU, memory access, divide. And someday I hope to put a floating point unit in there. I haven't done that yet, but I show it on there just because I'm hopeful. And then you have the write back at the very end. So one of the things I need to verify or to make certain of all those execution units, only one is ever allowed to write back at any given time. It's just the way the CPU is structured. Other CPUs will allow 2, but here I could set, you know, here's a set of 3 different things that can write to the register file, and either they're all 0 or one of them is true. Can't never be 2 or 3 true at the same time. Here's another unique thing to the ZipCPU. Once an instruction hits the memory unit, conceptually, it cannot be rolled back. So if you want to do a load, you have to make certain that any conditional execution, whatever, that would turn that load on or off is completed before the load starts. This is designed to allow memory operations that have other consequences, like reading from a transmit queue or something from hardware. Let's see. Operands going into the execution units. This is one thing that really gave me a hassle. There's a lot of code working through the bypass of the execution units to make sure the right stuff goes in. So it's got to match the register state. The wishbone interactions have to follow wishbone properties. Instructions from the prefetch are constant until accepted. This applied to several stages. It wasn't just the prefetch. But these are just sort of some of the properties I started with just to get myself going into what this would take. Let's see, I already did that one. So real quick on the instruction cache. I like to think instruction caches or caches in general are really easy to verify. There are 3 properties you need. So to start, you just pick an arbitrary address and an arbitrary piece of data. I'll show the instruction cache version. The data cache isn't much different. Number 1, you assume anytime you get an acknowledgement and the returned address you're expecting equals this address, you assume the data matches. Number 2, you assert that if it's in the cache, it must match the data. Number 3, if you return an instruction here and the instruction's address match that address, then again, you assert, so we've got 1 assumption and 2 asserts now, assert that the data's right. This is easier than I thought it would be. The cache is hard, okay? Let's be honest. If you built a cache, it's not simple to build a cache. This verification is easier than building the cache. There we go. When you get to an instruction cache, another one's very powerful is you just cover the valid trace. And if you're just starting out, you say, give me any trace through this instruction cache that gives me a valid return on the cache. It's amazing how many bugs you can work back and forth with the formal tools to find a lot of what's going on through there. You've got to see a reset in your trace. You've got to see the CPU request an instruction. It's got to get a cache miss. It's got to fill the cache line. It's got to all in one trace. And oh, by the way, that's just one line of formal verification stuff made that happen. I could do a whole lot more. This just gets me started real fast. With the data cache, I did the same methods. You have to modify them a little bit because the value might change. And I had one bug in simulation. I felt like I was doing so good. I verified that it would return the right value, but I never verified that it would return a second value. It left the I'm busy flag high after returning the value. Oh, got close. But it was only the one bug. So the formal verification got me most of the way there. And I have cache bugs are really just so hard to find. So formal methods found, in my case, most of the bugs. The tools can return really quickly. We're not talking hours and days for most of the proofs. The trace, it goes directly to the bug. You don't have to go looking through 100 gigabytes of trace file to find a bug. Actually, I'm usually working between 1 and 10 gigabytes when I deal with traces. When you're using the formal tool, the trace is maybe 10 kilobytes. It might have 20 clock cycles in it. That's all you have to examine to figure out what's going wrong. When I got to the full ZipCPU, I was only doing 18 clock cycles was all that it took to prove the whole CPU. Let's see, minimum logic steps, I mentioned I could do it in 18, but from this data cache, so I can't remember what it was for the data cache, but for the data cache, I still needed simulation when I was done. So it got me most of the way there. In the instruction decoder, here's my first lesson learned. I had a whole lot of, if the last instruction was this, then the output of the decoder should be that on the next clock cycle. So if I'm on the last, here's the instruction I'm looking at, then here's what my output should be. The problem I had was the check doesn't apply anytime the pipeline is stalled. So if the data cache isn't going through this transition because the pipeline is stalled, the formal tools aren't checking anything. And so this allowed it to get into states that it shouldn't have been in. Had I just kept that instruction around one more clock cycle and then verified this DCDR against the net clock cycle, I wouldn't have had this problem. If I do this again, that's what I'm going to do. That's what I just said, verify the outputs instead of the transitions. That check would apply even if the pipeline is stalled. Okay, the next thing that just got in the way was the debug port. I said, I'm going to be so smart, I'm going to put a debug port into my CPU, and right here, if the ALU isn't being used, if it isn't right, I'll stick my debug port there, and it's going to go right into the reg file. And I'm going to stop things right at that point if I ever go into debug mode. What the formal tools showed me that I wasn't expecting is, if you've read something from the register file, added an immediate to it, and then dumped it right here, and so you're waiting for permission to get into the ALU for the debug port to be free, it'll write to that register file and invalidate this, and I had never put that logic in to invalidate it. This is one of those things that I found, but I wouldn't have found without the formal tools. Yeah, no end of problems. I thought it was so simple when I was building it. I discovered it wasn't nearly as simple as I thought it should have been. The problem was the pipeline. My solution was anytime you rewrite something to that debug port, just reload the pipeline. You're slow anyway. You don't have to be fast when the debug port's in process. Can anyone else agree with this one? All right. Abstraction. So this is one of those things I really want to write about on my blog. I haven't gotten to it yet. But the idea basically is, let me replace the multiply with an abstract multiply. And all this abstract multiply is going to do is it's going to return a number that the formal tools are going to select. It may or may not be the right value for the multiply. I know that the multiply works. I just want to know that it works inside the CPU. So I would replace the multiply with something that I called an abstract multiply, which would say that if either of the incoming values was 0, the result should be 0, otherwise it should not be 0. The solver picks the result. Solver picks the input and output values. And up inside the CPU, the whole thing would fail. And so this works real nicely for formal verification. It requires you to maintain the signaling and prove the CPU logic works. Made things pretty easy. My problem was the top level CPU was worked and proven, but I didn't formally verify all the modes of the multiply itself. I got past the multiply with the abstraction, but yet there was a bug in the multiply that I didn't catch. Lesson learned, create a property file for every interface that defines both sides of the interface. When you're proving the CPU, you use one half of that property file. When you're proving the multiply, you use another. That would apply to the prefetch, the decoder, the ALU, and the memory unit. Still haven't done that. This is what I would have done because I got caught on that interface. Next piece is aggregation. One of the real things formal tools, the basic lessons of formal tools never go over aggregation. It's not your first lesson. The problem is I've got several components to my CPU, and each of these components has assumptions and assertions within it. If I just put all of these pieces together, these assumptions are going to keep it from finding problems. So what you have to do, so I proved every component before beginning. That's the first step. But then what I did was I swapped the assumptions and the assertions. So if it was an assumption before, it became an assertion. If it was an assertion before, it became an assumption. So before, this would be saying, as long as this is true, prove that that's true. Now it's saying, prove that those assumptions are actually true in the first place. I got caught on a couple of assumptions I'd made within, for example, the prefetch that didn't hold. So this gives you a whole new set of CPU properties. It turned out I had some assumptions within my memory controller that took a bit of work to prove. Lesson learned, the submodule assumptions aren't givens. Manage those interfaces. Make sure both sides of the interface maintain the same properties. They need to be proven as well. So the ZipCPU was built with a multipass verification idea. So the idea is if you've got a whole set of assertions, you start with your assumptions, then you prove the assertions on the first step. Then when you go to the second step, I don't need to prove that first set again. I can just prove the second set. I could have gone on with a third. I only went with 2 for the CPU. Anything you've proved can be an assumption to prove something more. It must be done in order. You can't assume stage 1 up here until you've first proven it via assertions. And any logic change will send you back to the beginning. So what happened? I had 2 passes. I used one just to prove the component assertions. I had a bunch of ad hoc assertions and some pipeline assertions. And then on the second pass, I said, let's pick a specific instruction and let's follow it through. The reality was, that was a waste of time. The solver picks a set of instructions in the first place. If I had just followed those instructions on the first pass, I wouldn't have needed a second pass. And then I had to prove most of the logic anyway on the first pass, just because proving the stuff within the submodules was that difficult. Okay, what did I find? Shall we have some fun here? Bus error on an instruction read didn't necessarily halt the CPU. So if you try and read something that's not memory, the CPU should halt with a bus error. It wasn't. Interrupts might break the compressed instruction words. Yes, the ZipCPU has instruction words. The debug register, I talked about the debug register. If you have an instruction word on the ZipCPU, it's not 2 separate instructions. It's one word with 2 instructions between it. They go as a unit. That gets me out of all kinds of painful logic of trying to handle misaligned instructions. Everything's always aligned. Well, if you halt mid-compressed instruction pair, you can't. Divides would start before the multiply finished. So if you had an output of a multiply that you wanted to stuff into a divide, it might get started. Break instructions would be, I'm glad I did this. It was very useful. Lesson learned. Before using, I did a lot of programs with the ZipCPU. I applied the CPU to many FPGA boards. Debugging on an FPGA is difficult. Can I get an amen, brother? Simulation requires lots of gigabytes of traces. With formal, simulation alone didn't find these bugs. Even an incomplete proof was valuable. What you don't prove will surprise you. Simulation requires gigabytes of traces versus formal was about 20 to 60 kilobytes. Still needed simulation when I was done. And you can take a simulation symptom and recreate it within the formal tools to see what would cause this to ever happen. If I had to do it over, I'd start with formal. Formal seems to have such a benefit when you're just building something in the first place. It's an amazing benefit to get something right the first time. I would do formal before I ever touch simulation. I wouldn't do it the other way around. And I definitely do it before code bloat. Code bloat just adds so many options that then need to be proven. It makes the proof all that much harder to do. All right. Did I finish in time? I'll take some questions.
Thank you.
You had mentioned if you had changed the code, you'd have to start back from the beginning on your formal
If you do the
test.
two-pass, yeah.
So is there a way to set up your formal verification so that you can keep both sets, so that if you're running your formal verification, you go in and make a change, your tests are just going to run again, or you need to go in and physically modify the code?
So the way I've got the make file set up is if certain code pieces change, that proof needs to be redone based on those code changes. If you try and do it without redoing the whole proof, you will get something other than formal verification. That's what formal verification does. It goes through everything and proves everything. I had problems where I had proved the second pass without the first, and then I found a bug in the first pass, and it's like, why did I waste the time on the second pass? You get the idea. Second question. Oh, I'm sorry.
Hello. I was wondering, did you use or have you used fault injection or any other techniques to sort of prove the completeness of your assertions and assumptions?
I have not. That will be another experience for me when I do. Perhaps I'll come back and discuss it.
Any other question? Jeremy.
Or just a comment. I like your quote there, but I would commend to you for a formal verification, Acts chapter 2, verse 12.
Thank you very much.
Someone can go and look that up.
I will be doing that as soon as I get down here.
Anybody else?
Sure.
Please.
Which tools were you using? You might have covered it in the beginning, but...
SymbiYosys.
SymbiYosys.
This is all done with SymbiYosys.
Yeah, wow.
What do you call it? The engine I used was the Yosys engine, sometimes called Yikes, depending on whether or not you want a hard C or a soft C. But yeah, this was all open source. I didn't pay a dime for any of these tools.
Cool. Does it emulate proprietary solutions, or is this a brand new solution? Sorry, I've kind of...
It uses the formal verification constructs that are part of the Verilog, or actually the system Verilog standard.
Okay.
So the SymbiYosys only uses the immediate verification constructs. There's another version that uses the full range. Another version of SymbiYosys. The version I was using just used the immediate constructs.
And what got you into exploring all of this?
Very good question. What got me into exploring this was I was asked to try it out. And so in standard human fashion, I said, I know everything I'm doing is right. Let me just prove this tool is messed up, and just be nice to the people who asked me to try out this tool. And so I gave it, my FIFO. What can be wrong with a FIFO? A FIFO is just a simple construct, and I started writing some assertions, and I discovered my FIFO didn't work like I thought it did. Because the formal tools had the ability to imagine situations that were beyond my creativity to put in the test set. And so, okay, well, it found a bug in my FIFO. Let me try it in something else. It found another bug. Okay, let me try it in something else. And pretty soon I feel like my credibility is on the line because I keep finding latent bugs in my own code. And so I started working through all of my code trying to find all the bugs. And then, well, can you do this one? I mean, this really, the ZipCPU, proving a whole CPU core sounded to me like the big cojones. Can you actually do the, swallow the whale? And yes, you can. Here's some lessons I learned in the process. I could do it better a next time if I were starting over. But I did get to the end where it worked.
Well done.
Thank you.
So do we have a last question? How long was the question?
To prove everything right now may take a half an hour to an hour. The formal process of putting everything in was maybe 2 to 4 weeks. It would have been a lot faster if I had started with the formal when I first started the core. One of the problems is as I've moved this core to hardware after hardware after hardware, I've kept having to trim it or expand it. And so it's got all kinds of features within it. You can use this feature or that feature, pick what fits on your, and I had to prove it for all the different features. SymbiYosys, if you're not familiar with it, has the ability to say, I want to prove it where the parameters are this, this, and this. And so if your core is parameterized, you can prove all of the assertions given these parameters are true. So.
Okay. Great work. Thank you very much.
Thank you.